last lecture, we have completed modeling of distribution system components, and in this particular lecture we are going to start distribution system analysis. And initially we will start with load flow analysis, and then we will go to the short circuit analysis. So these tools are basically load flow analysis and short circuit calculations. So we have seen load flow analysis and short circuit calculation in our BTech course. However, for distribution system, the methods or algorithms used for load flow studies as well as short circuit calculation, they are different. So in this particular chapter, we will see load flow analysis and short circuit analysis for basically distribution systems. Now, if you go for load flow studies, the load flow study is prerequisite for many planning as well as operational problems. So these problems like network reconfiguration, made for loss reduction, load balancing or service restoration, we need load flow studies before doing it. Then for hold to hour control, this is basically required for voltage profile improvement in a distribution system or hold to hour optimization. In this case also you need load flow study results so that we can arrive at proper hold to hour control in a distribution system. Then in a planning studies, when you are placing DG or capacitor, maybe it for loss reduction or renewable integration or reactive power management or voltage profile improvement, we need load flow studies results so that proper placement of DGs or capacitor will be done. Then for placement of regulator or control setting of regulator, we need load flow studies. We have seen that in case of placement of regulator or when you are setting, when you are doing settings in this line drop compensator circuit, those are basically based on load flow studies. And we have seen that all these tasks should be completed without violating your system constraints. So while doing this load flow studies, we can also incorporate your constraints of the system so that constraints will not get violated. Therefore, your load flow studies will always be integral part of whenever you are solving these kinds of issues. So flow studies will be integral part of those studies. Now in our BTech course, you might have studied methods like Newton-Raphson or Gauss-Seidel. So these methods like Newton-Raphson or Gauss-Seidel, we can use it for a distribution system also. However, the X by R ratio of distribution system is very poor, and because of this, convergence of these methods is very poor, means they will converge very slow, because in transmission system we know that X by R ratio is very high, and because of this X by I ratio which is very high, there will be decoupled effect, means your P will be basically depend on angle of the voltage, that is delta, and Q will be mainly depend upon your voltage difference delta V. And because of this decoupling effect, your Jacobian matrix of Newton and Raphson will be diagonally dominating, and because of this diagonal dominance, it will converge fast. However, in case of distribution system, this X by R ratio is very poor. So as I discussed, program design for power systems normally assume that X by ratio is high. Therefore, a program developed specifically for distribution system will be more efficient and simpler than those developed for high voltage. So we can develop some different algorithms for distribution system which will be more efficient, as well as they will be specifically for distribution system. Thus it will lead to low memory requirement and good accuracy. So these simple algorithm or specific algorithm for distribution system, they will be lead to low memory requirement and good accuracy. Moreover, they will be simple in implementation and has good convergence speed. So as I told you, when you are going using Newton-Raphson or Gauss-Seidel method for distribution system, their convergence is slow. So we can develop some other methods whose implementation will be simple and will give good convergence, or it will converge fast. So, load flow studies will be required for studying balanced as well as unbalanced systems. So, generally we have seen that distribution systems are unbalanced. So, many cases we need to study unbalanced systems. Also, we can take the advantage of systems, distribution system which are radial, mainly radial as well as weakly meshed. So, we will develop the algorithm for radial system or sometimes weakly meshed systems. Now, let's start with one classical algorithm used for distribution system analysis or load flow analysis of distribution system, which is called as backward forward sweep load flow algorithm, which is classical one for distribution system analysis. Let us see how it works. So, in this case you are having say simple 2-base system like this, then there are 2 loads are connected. Say this load is PL2 plus JQL2 and this load say PL3 plus JQL3 and this is bus number 2, bus number 3 and this is your bus number 1 source bus. The voltage at this bus is given and will remain constant on all iterations. So, we are keeping the bus of this voltage at this bus 1 will be constant at say Vs angle 0 degree. Now, this backward forward sweep algorithm will work like this. Initially, we assume that voltages at bus 2 as well as bus 3 which is equal to voltage at source bus. So, V2 we can say it will be Vs angle 0 degree as well as voltage V3 will be equal to Vs angle 0 degree. So, this if you are putting bar on this it will be actually vector quantity, but for brevity many times I will not write this bar here. So, I will just write V2, V2 will be your complex quantity or vector as well as your V3 will be your vector. So, in this case what we can do, we can calculate the load currents at each buses. So, load current as bus number 2 which will basically I2 current will be equal to PL2 plus JQL2 divided by your Vs angle 0 degree, because we are assuming voltage at that bus is Vs angle 0 degree and we are taking complex conjugate of it. So, that will get the current I2. Similarly, we will calculate current I3, I3 will be equal to PL3 plus JQL3 divided by Vs angle 0 degree, because in this case also at bus 3 we are assuming voltage is Vs angle 0 degree. So, a complex conjugate of it. So, current I23 will be equal to just load current at bus 3 which is I3 and then current I12 will be equal to I23 as it is if you apply KCL at this point. So, I23 plus current which is flowing at this load current flowing at bus number 2 which is we have calculated which is I2. So, I12 will be equal to I23 plus I2. So, this is called as backward sweep. So, all the line currents we are calculating by going backward from your end nodes and we are reaching till your first node or source node, and then voltages will be calculated starting from source node. So, I can write the equation for V2 will be equal to V1 which is basically Vs angle 0 degree minus drop which is happening across this particular line which is impedance is say Z12 and current flowing through this is I12. Similarly, I can calculate voltage V3 will be equal to V2 minus Z23 into I23 and this is called as forward sweep. And in this case, we are calculating voltages in forward direction starting from your source node, and then we are reaching to the end node, so that we can get the voltages at say from V2, then from V3, and then you can use this V3 updated voltage V3 into when you are calculating voltage V3 here. Then now and remember that here these V3 as well as V2, they are complex numbers as well as you can say they are phasors. For brevity, I have not given bar on it. So, using this I can calculate again current I2. So, current I2 will be equal to, again, loads I am considering constant power loads. So, if these loads are not constant power loads, or if they are a mixed load, this load also need to be updated in each iteration. However, in this case, since I am considering constant power load, the loads will remain constant. So, it will be PL2 plus JQL2 divided by your new voltage, which you have got is V2, and then you have to take star of it. So, V2 will be having some angle that I have not written it here, and then similarly I can get I3, which will be equal to PL3 plus JQL3 divided by your V3 star. Now, to differentiate between these I2 and I3, I can say these are I2 and I3 at first iteration, this I23 and I12 at first iteration, and these voltages which you have got is at the end of first iteration. Now, here we have started second iteration. So, at the second iteration, this is say current at second iteration, this is current at second iteration, and then I23 at second iteration will be equal to again I3 at second iteration. So, this first I3 at second iteration, and then I12 at second iteration will be equal to I23 at second iteration plus I2 at second iteration, which you have got it here, and then again voltages will be updated. So, V2 at second iteration will be equal to Vs, this voltage we are keeping constant, so it will not never change. So, Vs angle 0 degree minus Z12 into I12 at second iteration, this was this first iteration. So, I just have to write first iteration here, and this is Vs, it will also at first iteration, and then V3 at second iteration will be equal to V2 at second iteration minus Z23 and to I23 at second iteration, and we have to keep it repeating this pattern till we converge. So, how to check the convergence? Let us see. So, we have got values of V2 at say kth iteration, and then we have got V3 at kth iteration by doing many iterations, and we know the values of V2 at k minus 1 iteration also, and V3 at k minus 1 iteration also. Then error of voltages at node 2 or at kth iteration will be equal to mod of V2 which we have got at kth iteration minus V2 which we have got at k minus 1 iteration, and then error in 3 voltage at node 3 will be at kth iteration will be equal to V3 at kth iteration minus V3 at k minus 1 iteration and its mod. And then you see, so in kth iteration we are getting these 2 errors here. Then to get maximum error, so maximum error at kth iteration I can say E max, which will be equal to maximum of E 2 k and E 3 k, means you have to get the maximum value of errors, you have to from all the errors. So, in this case since there are 2 buses, so you have to get the maximum value from these 2 buses which is E max. Now, then you can compare this E max with your threshold value. If this E max is less than or equal to your tolerance limit which say epsilon. So, whatever tolerance limit we set, if it is less than this, then we can actually print your results. Now, let us see the steps in this particular algorithm, that is backward forward sweep load flow algorithm. So, for any general type of distribution system, say your distribution system is something like this, you are having some buses, and then there are some branches, say. Here also there are some branches. This is first node, second node, third node, and then there are many number of nodes. Say this node is M, this node is N, and say there are n number of nodes into the system. So, total number of nodes say equal to n. Now, let us see the steps. So, voltage at the first is, I am assuming it is Vs angle 0 degree as per our philosophy algorithm, and which will never change in during the iteration, it will remain constant. So, step 1 is initialization of voltages. So, in this case we will initialize voltages of all the buses. So, I can say Vj at 0th iteration will be equal to Vs angle 0 degree, and this will be defined for all j's starting from 2, 3, and it will go to up to n. So, basically we are assigning all the nodes which are j, which is changing from 2 to n, we are assuming the voltages should be Vs angle 0 degree, that is your step 1. So, this is your step first. Then step 2, initialize your iteration count. So, iteration count initialization. So, here I am getting k is equal to 1. So, it is first iteration. Then step 3 we have seen, we have to calculate your load currents. So, load current equation we have seen Ij, load current at any jth bus at say kth iteration. Now, in this case, since if it is iteration number 1, it will k will be equal to 1, will be equal to PLJ, which is basically real part of the load, and then J QLJ, imaginary part imaginary part of the load at jth bus, divided by Vj, voltage at jth bus, but that is calculated at k minus 1, because we do not know that voltage here. So, that is calculated at k minus 1 iteration, so earlier iteration. So, in this case when you are calculating for say k is equal to 1, so this first iteration, and then you have to use the voltages which are basically at k is equal to 0, that is Vj 0, which is we already initialized, and then you have to take the complex conjugate of it, and this we have to do it for all the j's ranging from 2, 3 up to n. So, load currents at each bus will be calculated by this equation, which is basically step 3. So, step 3 is basically load current calculation. And then your step 4 is basically you have seen it is backward sweep, where we are calculating the branch currents. So, when I am calculating say I m n, which is basically branch current which is flowing between branch connected between bus m and n, will be equal to at kth iteration will be equal to I N, which is basically load current at nth batch, which is calculated at kth iteration. We already calculated it in step 2, plus summation of, so this summation of all the currents of branches emanated from bus N. Then in step 5, we have seen it is forward sweep, and in forward sweep we are calculating voltages at each bus. So, voltage any nth bus, voltage at any nth bus at kth iteration will be equal to, so when I am calculating voltage at nth bus, voltage of mth bus will be already calculated. So, which will be known because we are actually starting from source node and we are going towards leaf nodes or end nodes. So, before going to the nth node, we already calculated the voltage of mth node. So, voltage, then voltage of mth node, which is already known, minus impedance of this branch, say ZMN, and current flowing through this branch is IMN at kth iteration, which we already calculated in step 4. So, this will be available from step 4, and this V voltage of bus M we already calculated in same step, but before calculating voltage at nth node. So, this is how we can get the voltages at each bus using your forward sweep, and then in step 6 we are calculating error. So, error at any jth bus. So, this will be again repeated for all j which is going from, or all n's which are going from 2, 3 up to n. So, we basically using this we are calculating voltages of each bus, and then E j error in voltages of jth bus in kth iteration will be equal to mod of V j bus voltage of jth bus at kth iteration minus voltage of same bus at earlier iteration k minus 1th iteration, and we are taking the mod of it. So, here also this will be repeated for your j going from 2, 3 up to n, and so after getting errors of voltages in each of the bus, you can get the maximum error. So, in step 7 we will get maximum error. So, E max of your kth iteration will be equal to maximum of all the errors. So, here we are getting all the errors, like we are getting error in 2 of kth iteration, error at bus 3 at kth iteration, error at bus 4th at kth iteration, we have to error at nth bus and kth iteration. And when we get maximum error, so these are the error nothing but the error at each bus, and when we get maximum error in step 8, we compare that maximum error with respect to your tolerance value which you have selected. So, this if this E max at kth iteration will be less than or equal to epsilon, which is basically tolerance value which is selected. If this condition is getting satisfied, so I can write if statement here. If this condition is getting satisfied, you are converged with results. So, print results which are correct. Else, if this condition is not getting satisfied, update the iteration count, update iteration count. So, we can make k is equal to k plus 1. So, now you are going to next iteration, and then you have to go to and go to step 3. So, step 3 we have seen, step 3 is here. So, again we will calculate using the voltages at k minus 1th iteration, early iteration we will calculate your currents at each bus, load current at each bus, and then we will calculate branch currents by going backward towards the source node. We will calculate currents in each branch by adding this one. So, this will be run for all Mn branches in the system, and then we have seen we have to use forward sweep to get the voltages. So, we will go to step 5 to get the voltages and then get the error in each bus voltage, maximum error from all the errors in all the buses, and this maximum value will be compared with tolerance value. If it is lesser than tolerance value, you have to print the result. If error is more than tolerance value, you have to still keep iterating. So, you have to iterate the update your iteration count to k is equal to k plus 1, and you have to go to step 3. So, you will be in this loop till this condition get satisfied. So, this is your backward forward sweep algorithm of a load flow. In next class we will see one example of this, and then we will go for 3-phase backward forward load flow algorithms. Thank you.